Okay. Geçen ders topoloji sine curve'ü yapıyorduk. Bunun connected olduğunu gösterdik. Bugün de path connected olduğunu göstereceğiz. Path connected olduğunu göstermeden önce şuraya bir tane şey sığdıracağım. Bir tanım, çünkü ispatın içinde geçiyor. Yani en azından benim vereceğimin. Şuraya definition diyeyim. X bir tane topological space olsun. Space. Okay. And let X be any point. Set EX to be the following union. The union of, okay, all connected subsets of X containing X. So what is EX? EX is the following subset. So it is the union of all connected sets containing X. Well, these subsets A's, they all contain a common point, which is X, and since they are all connected, their union is connected, right? Since all A's in the union contain the point X, so they have a common point. In other words, they have a common point. Okay. EX is connected. Okay. Well, we know that if we have a connected subset, then its closure is also connected. We know that ya da şöyle diyeyim ilk önce. Note that EX is the largest connected subspace, connected subset, let's say, of X containing X. However, we have something slightly larger than that. This one is also connected. Because closure of any connected subset is connected. But EX is the largest one, and okay, EX is of course contained in this, and hence EX is equal to its closure, so that EX is closed. Okay, it's a closed subset. This EX will be called the connected component of X containing X. EX is called the connected component containing X. Okay, connected component of X containing X. Of course, if Y is in EX, then EX is equal to EY, right? So because if let's say EX is this and EY is this, and they have a common point like this, then the union of EX and EY is also a connected set containing X. Therefore, EX union EY would be equal to EX. It means that EY is contained in EX. Similarly, EX is contained in EY. Therefore, these connected components are the same. In other words, for any xy in X, we have either these components are the same or they are disjoint. Okay. Since these are disjoint subsets and every point is contained in one of them, X is a disjoint union of these closed subsets. Okay. In particular, X is the disjoint union of its connected components. So we have this. X is a disjoint union of these gadgets. Okay. For some X's, these are the same, but any two of them, if they are not the same, are completely disjoint. Okay. So writing this way is a little bit problematic, but you understand what I'm saying. Some of them, for some X's, you may have the same component over and over in the union, but so you have components like this. Okay, so this is actually something like this. This is EXI. I is in some index set, and index set is chosen to be so that you have one I for each connected component. Okay. All right. And important thing is that, well, actually, I'm not sure if it is that much important, but each EX is closed. Okay. Each EX is closed. Can we say that each EX is open? Well, not in general, but let me remark here. If the number of components of X is finite, so if there are only finitely many components, then X is something like this, right? EX1, disjoint union EX2, disjoint union, let's say EXN. But then, so EXI is equal to what? This is just X minus the union of EXJ's, J different than I. But there are only finitely many such closed sets. So this is a closed set. It is a finite union of closed sets. Therefore, it is closed. And this implies that EXI is open. So if there are only finitely many components, then this topological components not only closed but also open. Okay, now let's come back to the proof of the claim. Sorusu olan var mı buraya kadar? Şurada yapayım. Proof of the claim. Şimdi ne dedik? Bu eğri connected olsun dedik. Pardon, pet connected olsun dedik. Şu eğriyi şuraya bir daha çizeyim. Yani pet connected olmadığını göstereceğim. Eğri şöyle bir şey. Okay. Now let's assume for the moment that this space is path connected. Assume on the contrary that buna x mi demiştik? Evet. X path connected. Well, there are 2 points on this space. Let me mark them. Well, there are infinitely many points, but 2 of them are these. One of them is 0, 0, and this one is 1 over pi. Sorry. No, it is not this one. Sorry. It is this one. The first 0, 1 over pi. Okay. And since I assume that the space is path connected, there should be a path joining these two. By assumption, there is a path. There is a, of course, continuous path. Gamma defined on, let's say, 0, 1, so that gamma 0 is 0, 0, and gamma 1 is 1 over pi 0. So I have a path joining these 2 points. Okay. Well, let the components of this, right? This is a path in R2, so it has 2 components. These are just actually projections from R2 into R. So these are the components. And where, of course, xt and yt are continuous real valued functions. Continuous in this standard topology, of course, continuous real valued functions with what? X0 is this value is 0, and x1 is 1 over pi, this one. Okay. Well, then, since then the topological component of the open subspace or subspace x inverse of 0 infinite. So x is a function from 0 1 into R. I take inverse image of this subset, okay? This subset, the open subset containing 1. Well, 1 is contained in this inverse image because 1 over pi is a positive number, so it is here. Therefore, 1 is in the inverse image, right? 1 has the form okay, where 1 less than a less. Yes. Okay. Why is that? X'in pozitif olduğu yerlere bakıyorum ve bir noktasını içeren şeyine bakıyorum. Şimdi X'in pozitif olduğu yerde bir noktasını içeren aralık birden başlayacak. Connected olacağı için bir interval, değil mi? Yani şuna bakıyorum. 0, 1 içinde diyorum ki x'in 1'deki değeri pozitif. Dolayısıyla 1 bunun içinde. Bir noktasını içeren bu open set'in connected component'unu istiyorum. Connected component bir interval olmak zorunda. Bir yere kadar gelecek. Sıfıra kadar gelemez çünkü sıfırdaki değer 0. Dolayısıyla 0 bunun inverse imajında değil. Bu inverse imajda değil. Bir yerde durmak zorunda. Niye open interval? Niye closed değil? Çünkü bu kümenin kendisi open bir subset. Yani 0, 1'ın içinde open bir subset. Gerçi onu şimdi yine söyleyeceğim. Yok. O böyle ama şunu biliyoruz. Note that, yani bu open olduğu için bu set open olduğu için topological component'ı open olmak zorunda. Şunu diyebilirsiniz. Topolojik komponentlerin yukarıda biz closed olduğunu söylemiştik. Bu niye öyle değil? Çünkü bu uzayın subspace olarak closed bu. Ama şey olarak R'nin içinde open olmalı. Yani 0-1'in topolojisinde open olmalı. Çünkü bu nesne open. Evet. Şimdi note that x of a must be 0. Why is that? Because, yani eğer a'daki değeri 0 olmasaydı, if it were positive like this one, then I would obtain another interval around a, and here the function x would be still positive, but then the values where x is positive would be wouldn't stop at a, but it would continue a little bit more up to this point. Okay, therefore x of a must be 0. Okay, because if x of a is positive, then the component would be bigger than would be şöyle diyeyim. Şöyle olmak zorunda olurdu. Where b is greater than a. But of course that would be a contradiction, right? If this is the component, then it should stop there. The values where at which x takes positive values. Okay, so x of a is 0. Ya aslında bunu şundan da biliyoruz. A is not okay. X of a is 0 since x is not a is not in this interval. So right, this is an open interval. Therefore, a doesn't belong to this inverse image. In other words, at a, x doesn't take positive value. So I have this, sorry. B A'dan küçük. Evet, haklısın. Evet. Tamam. Bir şurada, A burada. Eğer burada pozitif olsaydı biraz daha aşağı inerdik. Tamam. Çok sağ ol. Okey. Şimdi sonuna geldik. However, for any t in a comma 1, we have xt is positive, right? Because this is the interval. This is an interval in the inverse image of 0 infinity. Therefore, all the points here are mapped to positive numbers. So, and thus, I can write this y of a, which is limit of yt as t goes to a from right. I can write this because x and y are continuous functions. But when x and t are positive, sorry, when x is positive, y is equal to sine 1 over xt, right? Because I have this is my space. When x is positive, I have only the y-axis. But when x is when x is 0, I have only the y-axis. When x is positive, I am on the sine curve. So here, this value should be on the sine curve. So I have this. Okay, but when t goes to x goes to 0. Therefore, this limit is just the limit of sine 1 over x as x goes to 0. And this limit doesn't exist. Where the last limit does not exist. Okay? So that's the contradiction. Y of A is a real number, and it cannot be the limit of this expression. Why did we arrive at this contradiction? We arrived at this contradiction since we assumed that there is a path joining these 2 points, right? I assume that there is a path joining these 2 points, and that's the uh, assumption that caused this contradiction. Hence, there is no path joining 0, 0 to 1 over pi 0. In other words, X is not path connected. The proof in the book is a little bit different, I guess. I don't have it in mind. You can also read that one. Anyone is okay. Okay, so, but let me give you another example similar to this one, but slightly different. This time, let X to be the following object. So 0 comma y in R, union X comma y, X is positive and Y is X times sine 1 over X. Okay. So the only difference is that I have an X factor here. So the space is this. I have the y-axis as usual. Is this piece, and so this is the x-axis. There's another component of the space X. It is this one. You see, this is like the previous one, but since I have this extra X term here, the amplitude gets smaller and smaller. So aslında şöyle çizebilirim onu. This is y equals minus x. This is y equals x. And my sine curve is this one. X sonsuza giderken ne olur? X sonsuza giderken sinüs 1 bölü x bölü 1 bölü x eksi 1 bölü x kare eksi 1 bölü x kare kosinüs 1 bölü x 1'e gidiyor. Okay, so it's something like this. I don't know. I mean, it's probably something like this, but okay. As before, as before, both components are connected. So both components, red and blue, are path connected. Path connected, right? And actually, the whole space is path connected. Indeed, the whole space X is also path connected. Why is that? Because, take this point here and this point here, 0, 0. Neydi bu point? Şunu alalım. 1 bölü pi'ye 0 mıydı? Evet. There is a path joining these two. What is that path? Gamma t is this. Sıfırda 0. Pozitif olduğunda da işte t çarpı sinüs 1 bölü t t pozitifken. Yani eğrinin kendisi aldım. Okay. 0 koyduğumda 0, 0. 1 koyduğumda yok. Şöyle diyeyim, 1 bölü pi'den yapalım. 1 bölü pi koyduğumda 1 bölü pi 1 bölü pi çarpı sinüs pi 0. Okay. This expression is clearly continuous, so all I need to do is that it is to show that gamma is continuous at 0, but that's also clear. Gamma is continuous at 0 since what? Gamma 0 is equal to 0, 0, and this is the limit as t goes to infinity, no, not infinity, 0 of gamma t'ye eşit. Yani nedir o da? T virgül t çarpı sinüs 1 bölü t. Yani right? It's equal to this limit. As t goes to 0, this expression has limit. Therefore, I have a continuous path. Joining the origin to this point. It is the blue path. Okay. This space is path connected. Sorusu olan var mı arkadaşlar? Oh, sorry. So this is the last thing I'll do in this section, that R omega, in other words, the space of all real valued sequences with the product topology is connected. Why is that? Well, it is because of the following. Let A be the following subset. So I look at all sequences in R omega so that xn is 0 for all n greater than n0 for some n0. So the set of sequences which are eventually 0. A is the set of sequences that are eventually 0. So it takes maybe some non-zero values, but after some point on, it becomes 0. Of course, you know, this thing, note that A is homeomorphic to the following union. So it is union n from 1 to infinity, where Rn is identified with the subset of A with the following subset of A. Nedir o? Şu subset. Sequence'lar, isterseniz buna M diyeyim de notasyonda karışmasın. Xn'ler, öyle ki Xn dizisinin m'inci teriminden sonrakiler 0. Yani x m artı 1, m artı 2 ya da m artı k diyeyim, 0 tüm k'lar için. Dolayısıyla sadece m tanesi non-zero. Yani o zaman ben işte Rm'in bir elemanını alıyorum. Rm'in bir elemanını. Bunu nasıl göreceğim? Bunu sequence olarak göreceğim. M taneyi koyuyorum. Sonrasına hep 0 koyuyorum. Tamam mı? Dolayısıyla Rm'le bu tip sequence'lar aynı şey. Peki şunu biliyoruz. Rm is connected. Of course, here I have an topological embedding of Rm into A, right? It's a topological embedding. Is connected. So each element, each component of this union is connected, and they have the common element 0, 0, 0, 0, right? This constant 0 sequence, it is inside in each Rm. Thus, A is path connected. Sorry, A is connected, sorry. Okay, A is connected. Okay. Claim is this. Closure of this is equal to the whole space. And thus, R omega is connected. Because we know that closure of a connected set is also connected. So if I can prove that A closure is R omega, then I will be done. Proof? Well, proof is easy. How can you show closure is this? I'll just take any element. Take any xn in R omega. And I'll show that any open neighborhood containing this point, any open set containing this sequence contains some elements from this. But that's also easy. And an open subset, open, okay. Subset containing xn. Well, that open subset will contain a basis element. Okay. Then there is a basis element. Let me say this is your basis element of the form B, and it has this form, right? Basis elements are like this: A1, B1, cross A2, B2, some finite intervals, let's say A n, Bn, and after some point on, we should have all r's, right? Well, clearly, there is this element here. So this open set, note that B contains the element. Hangi elemanı içeriyor? Şunu içeriyor. İlk terimi A1 artı B1 bölü 2 olsun. İkincisi A2 artı B2 bölü 2. AN artı BN bölü 2. Ondan sonra da hep sıfır alayım. Right? B contains this sequence, but this sequence is of course in A, right? Because it is eventually 0. Okay. Hence, B intersection A is not empty, which implies U intersection A is not empty, because this is an element in this intersection, and it means that so that this element is in the closure of A, and this finishes the proof, right? I take any element in R omega and I show that it's in the closure. So A closure is R omega. Okay. I take any element here. I show that it's in this closure. So we have this. Okay. Any questions so far? All right. I already talked about components, so maybe I say something about ya da evet, tanımı vereyim. Yani bu tanım en azından şey. Section 25, sorry. Components and local connectedness. And local connectedness. We already talked about components, right? We have already studied components, topological components. Well, connected components. What about local connectedness? Let me give you the definition. We have similarly locally compact spaces and so on. So this is a kind of a generic definition where when you have some property, you can talk about local version of that property, like connected and then locally connected, compact, locally compact. So let me just state this. A space X is said to be locally connected at X if for every neighborhood U of X there is a connected neighborhood V of X contained in U. So locally connected means the following. Whenever you have a point, an open set containing that point, that open set may not be connected, but you should be able to find another neighborhood, an open set lying in U, and that should be connected. Okay. If this is the case, then we say that the space is locally connected. Similarly, a space X is said to be locally path connected if for every neighborhood U of X there is a path connected neighborhood V of X contained in U. Okay. Okay. Bir örnek vereyim. Şuna bakın. Topology sine curve'i düşünelim. So I have topology sine curve. Topology sine curve is not right path connected, but it is connected. Okay. Well, this space is connected. We know that, but it is not locally connected. Why is that? You see, if I choose a point here, choose a point here. Then and an open set containing this point is something like this. Actually, this red ball intersected with the space X, right? And what kind of object is this? You see, that's something like this actually. You have this gadget, and then you have lots of pieces like this. You have the y-axis piece, and then you have, pieces like this. Infinitely many of them. No matter how small you choose this red ball, there will be infinitely many, line segments like this, and they will be all disjoint, right? Therefore, this thing is right. So this is not connected, and it is not also path connected. So this space, hence X is not locally connected. Dolayısıyla locally path connected da değil. But I can actually make the space connected. How? Well, I mean, make this path connected. How? Just put another, path like this. Now it is path connected. So this is path connected. Path connected. Therefore, it is connected. We already know that it's connected, but it is not locally connected. Okay. Points like this do not have a neighborhood, arbitrarily small neighborhoods which are connected. Okay, let me stop here and then I'll continue in the next hour.